wherever is the Albert and the BA and BB models. Started doing some problems, so we'll do some more today. So this problem, so you're given, say, at some time unit, the degree of a node that joins a network at time 10 units is 50. So what is given is the joining time is 10. So our convention is to indicate something like this, or at least in this problem. The node joined at time 10, so this is the joining time. And its degree at some future time t greater than or equal to ti is given as 50. Okay, so joining time was 10 units, and we measure the degree at some time let after that it's 50. And so you want to now compute the degree of this node at time . So what's the degree of the node that joined at time 100 units? Okay, so if you read the question carefully, at some time unit t, the degree of a node that joined the network at time 10 units is 50. So there's one node that joined at time 10, and its degree at some future time t is 50. There's another node that joined at some time 100, and at the same time t, that you measure the degree of the first node, you want to measure the degree of the second node and see what it is. Is that clear? So the model is a BA model. Okay? So there are two time instances, time 10, one node joined, and its degree is, and at another time 100, another node joined. Now at some future time t, okay, you are given the degree of the first node is 50. You want to compute the degree of the second node. Okay, so that's what you want to find out. All right, so how to do this?
So is K first node and M second node?
K means degree.
Yeah, we're trying to find out the second degree, right?
Yeah, the degree of the second
Yeah.
node.
So
Okay.
the last class we heard that joining time. So the first node is here is K.
Again, I said K is degree. The first node joined at time 10, so that is its ID. So the joining time is ID of the node. Okay. All right. So the formula is Ki of t. What was the formula? M times t over ti raised to half. So this is the formula for the degree. That I is a joining time and also the ID of the node. So it's very simple now. You're given K10 of t as 50, and the formula is M times t over 10 raised to half. So K10 of t is M times t over 10 raised to half according to this formula, and it is given as 50. Now, what you could do is just split this. So this is the unknown part, and this is the known part, which is 50. So t over 10, I'm just splitting as t to the power half divided by 10 to the power half. Okay? So m times t to the power half is simply 5 times 10 to the power half. So you compute the value for this, that comes out to be like 158.1. So why I did like this? Because you have two unknowns, okay, and you're given only one equation or one value, so you cannot really find the two unknowns. So we club the two unknowns together as one term. Okay. So the second thing we want to find is, this is what we really want to find, and the formula for this is m times t over 100 raised to half. So 100 is the joining term. So again here, this m times t to the power half is the unknown term. We can combine them together like this. And this is 158.11 in the numerator. The denominator is 100 to the power of half. What is that?
Square root
of 100, which is 10. So that is 15.81. So this is the degree. So of course degree has to be a real number, so you could round it to the next largest value, which is 16. Okay, so that's the degree of the node that joined at time 100. Now you could see if the answer makes sense. This is according to the BA model, right? So the node that joined earlier has a larger degree, and the node that joined later has a smaller degree. Okay, it makes sense. Any question? All right. So again, BA model. So consider scale feed network that evolved according to this model. Now let there be two nodes P and Q, such that the rate at which node P acquires new links is twice the rate at which node Q acquires new links. So the rate at which acquires new links means the rate at which the degree of the node is growing. Okay, so last time we saw this. So this is the equation, and we differentiated this. Right? So when we differentiated this, what was that we got? So dki of t dt is m over 2 square root of t times ti. So this is the rate at which the degree of a node grows with time. Okay? So what is given is the rate at which the degree of node P grows is twice the rate at which the degree of node Q grows. Okay, so that's what is given in the problem statement. Now, if node P joins the network at time 100 units, we want to find the time at which node Q joined the network. So that's the only information given. So the joining time of node P. So you're given something like TP, the joining time, as 100 units. You want to find the joining time of node Q. Okay. So again, we have to kind of combine the different parameters because a lot of unknown variables here. Okay, so let us see what to do. So you are given this relationship. The rate at which the degree grows is twice. So let us substitute the expression. So for this one, it's m over 2, 1 over square root of ti is tp here times t. And it is 2 times, so this is the expression for q, m over 2, 1 over square root of tq times t. Is that clear? Just substitute the expression on both sides. So here we can simply cancel out the m over 2, and here the square root of t can go away. Okay, so that means this 1 over square root of tp is 100. So 1 over square root of 100 equals 2 times 1 over square root of tq. So it becomes very simple to calculate. So from there you can calculate tq. Okay, and it comes out to be 400 units. So the joining time of a node TP was 100 and TQ is 400. So you can see the node that joined the network earlier, its degree grows twice the rate at which the degree of the node that joined later grows in degree. Okay? Again, it makes sense.
Can you please repeat that?
So the node that joined earlier, its degree grows faster, according to the BA model, typically. So, and it makes sense here that TQ came out to be larger than TP, right? So it means TP joined earlier. So its degree is expected to grow faster than the rate at which the degree of TQ it's also given in the problem statement, the rate at which the degree of B grows is twice the rate at which the degree of Q grows. Okay? So if you get TQ less than 100, there's some problem in your calculation. So just try to see if the answer makes sense. Okay? Any question? Alright, so let us move on. So now the BB model. So in the BB model, this is the expression for the degree of a node that joined at some time Ti and at some future time T.
So the T will be, if the T is high, the degree will be low, it's opposite to each other, right? T and K. Yeah. Degree and time is opposite to each other.
No, it's not opposite to each other. So it's a joining time. So if the node joined earlier, its degree is going to be larger. So as I said here, so a node joined here and another node joined
Yeah,
here.
yeah, that's what I'm saying. Like if it's earlier means less time, then it's the degree is higher.
At some future time, its
And
degree is going to be larger than the node that joined later.
Yeah, that's what I'm saying. That
Yeah.
if the time is less, it will be higher there, and if it's going, the degree will be less.
Right.
Yeah, that's it.
Okay. That's the BA model. Now the BB model, you introduce a fitness parameter. So that will influence the rate at which the degree of a node grows. Okay. So the joining time Ti as well as the fitness parameter will influence the rate. Okay. So a node might have joined earlier, but if it's, so this example here, so the red node joined earlier, but its fitness is like 0.223, and the blue node joined much later, but its fitness is higher, 0.991. So eventually what happens, the blue node overtakes the red node. So at some future time T, okay, the degree of node, this blue node starts becoming higher compared to the degree of the red node. Okay, so that's what we actually want to find in this problem. So now before that, the exponent, it was a constant here, half. So this is the beta, the degree exponent, okay, or dynamic network exponent, that's the name. It's a constant in the BA model, but in the BB model, it is a variable which is a function of this fitness parameter eta. Okay, so if I don't give you what is that function, so beta is a function of eta I. So beta is the exponent, is a function of the fitness parameter eta. If I did not give you anywhere in the problem statement what is that actual function, you could assume it is same as eta I. If I want you to use a particular function, I will give you, it is like the eta squared plus 2 eta minus 1 or something like that, some function of eta. Okay? Alright, so here I have explicitly said let the parameter beta of eta I for any node I to be equal to the fitness of the node itself. So which means beta of eta I is simply eta I. Okay, so this is given. Then what else is given? So consider two nodes A and B such that the fitness of node B is twice the fitness of node A. So what does that mean? Eta B is twice eta A. Okay? So that's what that means. So eta B is twice eta A. So write down all the things that are given and then see what can you do. Now node A joins the network at time 10 units. This means the joining time TA is given as 10, and node B joins the network at time 100 units. Okay? Then what else? So if the degree of the nodes increase for every time unit, of course, when a new node joins, it tries to have a link with the existing nodes. What's the minimum value of time starting from which the degree of node B?
So zeta is the fitness.
Eta is the fitness.
Eta.
So what is the minimum time starting from which the degree of node B would always be greater than that of A? So this is like the figure I showed earlier. So you have node A joining at time 10, node B joining at time 100. So these are the joining times. Okay? And eta I values are not given right away, but what is given? Eta B is twice eta A. So it means a fitness of, so this has a high fitness and this has relatively low fitness. So the degree of A will grow like this, and the degree of B will eventually, so let us use the same red color. So A grows like this, and the degree of B will eventually overshoot the degree of A. Is that clear? Because B has a higher fitness. So what we want to find is this time. Okay? Because that's the minimum time starting from which the degree of node B is going to always be larger than the degree of A, starting from that time. Okay? So you are given the joining time of the two nodes and the relationship between the fitness. So based on this, we need to find the minimum time starting from which the degree of node B will be always greater than the degree of node A. Is that clear? So that's what you need to understand first, what is given and what you have to find. So so this is under BB model, so we have to use the degree formula for the BB model, which is this. So let us now try to simply write this based on the assumption given. So the degree of the nodes at joining time Ti at some future time T would be simply eta I, because beta of eta I is a function is same as eta I. Okay. So now let us so we want to find the time starting from which KB will be greater than KA. Right? So KB, if you want to use this formula here, is going to be M times T over TB raised to eta B, and KA is M times T over TA raised to eta A. Right? I'm just substituting a formula. So here, of course, the M can cancel out. And what is given is TA and TB. So TA and TB are given. So T over TB is 100 raised to eta B is greater than T over TA is 10 raised to eta A. So we really want to find this T, the time. Okay? Now eta B and eta A are not given right away, but the relationship between the two has been given. What is that? Eta B is twice eta A. So we need to make use of that relationship here and simplify this expression further. Is that clear? Okay, so let us try to just group the time term one side and the known term other side. So time, so if I just do one more step, so this is T raised to eta B divided by 100 raised to eta B is T raised to eta A divided by 10 raised to eta A. Right? So now bring this, do something called cross multiplication. So this is going to be T raised to eta B divided by, so this thing can come to the denominator, so that will be T raised to eta A greater than, this thing can go to the numerator here. So it is 100 raised to eta b divided by 10 raised to eta a. So I'm just rearranging. So this can come down and this can go above. Is that clear? So now what is that we can do? We can make use of the relationship. So I can just, so this is like t, so eta b is 2 times eta a divided by t raised to eta a greater than, okay? Eta b is again 2 times eta a divided by 10 raised to eta a. So what can we do? So this is t raised to 2 times eta a divided by t raised to eta a. So what that is?
1
T raised to eta a, like 2 minus 1.
A.
Okay? Greater than. So what can we do on this side?
90.
90?
No.
Where is 90?
No, sorry. 9.
Okay, so
Income.
of course the numbers are really going to be useful for us here, but you should be able to do such problems even if the numbers are not that easy to work with. Okay, so as a practice, pick some other 2 time units and try to solve this problem. Okay, alright, so let us see. So 100 can be written as 10 squared. Right? Now, so once you write it as 10 square, you have 10 square raised to 2 eta a. So that means that is 10 raised to 4 eta a. It's like 2 times 2. Remember, it's multiplication, not addition. So if you have something like 10 cube, it's going to be 3 times 2. Okay? So it's 10 square raised to 2 eta a, so divided by 10 eta a. So which means t raised to eta a, so this will be what? This is 10 raised to 4 divided by 10 raised to 1. So that is 10 raised to 3 eta a. Right? 10 raised to 4 eta a divided by 10 raised to eta a. So now the eta a is on both sides. So we can kind of cancel out eta a. So t has to be greater than 10 cube. Okay? So starting from time 1001. So until 1000, so 1000 is actually the time they will be the same. Okay? So starting from time 1001 or time greater than 1000, so that we can keep it as simple as that. So as we got the answer. So starting from time greater than 1000, eta kb will be greater than ka. The degree of node b will be greater than the degree of node a. Okay? So this is some important problem. So I can ask you something like this just by changing the numbers.
Sir, last point, beta value, about beta value. Beta of a?
The degree, kb.
Yeah.
So you wanted to
KB
find
is
the
always
time.
greater than ka.
So kb will be greater than ka, like here, starting from any time above 1000.
Yeah.
Okay?
Means always you said, as you always said, like the first time degree is less and then after it will be higher, right?
The degree grows as new nodes join.
Yeah.
Okay?
Yeah.
So in this model, in addition to the joining time, the fitness parameter will also have a say on how the degree grows. So that is this expression. Okay? So if it was a BA model, what will be the nature of the curve?
It's opposite. Like if the in the beginning it is high, right? The time when the time is low.
I will make a request. You did not come last time, so if you say something that will confuse others too. Okay, so let me draw and then you can understand. Okay, if it was the BA model, so this is under the BB model. So So it was a BA model, it has A and B joining. So it will be, so at some future time t, it will be like this. Okay? So as I said, according to this expression, so this is the rate at which the degree grows under the BA model. If the node joined earlier, its degree is going to grow faster than the degree of this node because the joining term is in the denominator. So the node that joined earlier will grow at a faster rate. So as you can see, this is a more steeper curve compared to this curve. Okay? Not only that, as time progresses, the rate at which the degree grows slows down. So the initial time after it joins in the starting time like this, during this time period, the degree grows at a faster rate. Then as time progresses, the rate at which the degree grows for each of those nodes slow down. How it slows down, it depends on the joining time. So it's like t times ti, so both are the denominator. So the rate at which the degree grows slows down for every node. And how much it slows down depends on the joining time. Nodes that joined earlier will grow relatively at a faster rate compared to the nodes that joined later. So at no time, the node that joined later will have a larger degree than the node that joined earlier, according to the BA model. Okay? Whereas in the BB model, since the fitness comes in, if the node that joined later has a larger fitness, it could eventually overtake the degree of the node that joined earlier, if the node that joined earlier especially has a lower fitness. Okay? Is that clear? So in this problem, we wanted to handle this scenario where a node that joined later has larger fitness, so it will overtake the degree of some node that joined earlier. So what is that time at which the node overtakes the degree of the other node? Okay? Is that clear? That's the difference between the two models. Okay, so let us continue.
So one question.
Uh-huh.
With degree and fitness. Degree, if the degree is high, the fitness is fitness and degree is opposite.
Fitness is a parameter like your weight
Okay.
or your salary or something. So it is a unique thing associated with each node. Okay. The degree is a variable thing. It changes with time. Okay. So the rate at which your degree changes with time depends on your fitness
Okay.
as well as your joining time.
Yeah. In BA model.
The fitness does not come in at all.
Okay.
So it's just a joining time
Okay. In BA.
in BA.
On BB fitness comes.
Yes,
And
fitness of the node as well as the joining time are used to determine the rate at which the degree grows.
in fitness time, if the latter, it will be the fit range will be good.
If the fitness is high, the chances are that if the node like this joins later at time 100, it will overtake the degree of the node A that joined earlier, provided that node has a relatively lower fitness. If
Okay.
node A has a very high fitness and node B also probably has same fitness, based on the joining time, you will always see node A to have a larger degree. Okay, so they both combine together and try to change the degree. Okay.
Okay, it's depends on the
It
joint.
depends on the values of Ti and Bi. You see where Ti and eta I are. Ti is in the denominator and eta is in the exponent. So of course, so that means if eta is larger, the exponent, it could increase the degree faster. Okay? And Ti is within the exponent in the denominator. So it's a combination of the two. It's a non-linear relationship. Okay? So if you want to have a feel of it, try for different values of Ti. So have a kind of for different values of Ti and eta I. So try to play with this, see how the T over Ti grows. Okay?
Over there is a T, you put question mark, right? Yeah, over there, yeah.
It means I want to find the time
Okay.
at which, starting from which the degree of node B will overtake. So this time, so this is the time axis.
Yeah,
Okay?
the joining time depends on the weight.
Joining time depends on the weight.
And there's a link between, you say, like joining time and weight, right?
Joining time and the fitness
Yeah,
are
yes.
independent,
Okay.
but they can together decide how the degree grows. Okay? So like your birth date and weight are independent, but together they can decide how your degree grows. Like that. So joining time is like the time at which the node joins the network. Okay? And fitness is like something that is unique about that node. Okay? Okay, so let us do this problem. So this is similar to the previous problem we did on BA model, where we had to combine the unknown variables. So let the degree of node A be 50 at time 100, and if the fitness of node A is 2, find the degree of the same node A at some future time 400 units. Okay? So first write down what is given. So you're not given the joining time, so note that. Okay, so what you're given is at some time t, which is 100 units, the degree of node A is 50. Okay, and the fitness of node A is 2. Okay, so here I did not give you the relationship between the function beta of eta I, but what I have given you is fitness of node A as 2. So since I did not give you that function, you could assume beta of eta A is eta A itself. So the exponent beta is simply 2. Okay. So what we have to find? The degree of that node A at some future time 100. So you are not given the joining time at all, it's unknown. Okay? So we have to handle that. So how to do this? So first write down what is given. So you're given Ka at some time 100 is 50, and Ta is of course the joining time. Okay? Then according to the formula, this is m times T over Ta square. So now if this is 50, we just rearrange the unknown. So Ta is not known, but T is known as 100. So m over Ta square. Okay? If you bring the 100 to the other side, it comes to the denominator. So it's 100 square here in the numerator, but if you bring it on this side, it comes to the denominator. So it's 50 divided by 100 square. So m over Ta square is 50 divided by 100 square. So I have this combined to one unknown now. Okay? So what we want to find is K, the degree at time 400. So according to the formula, that's going to be m times time 400 divided by Ta square. So that is going to be m. So if you just simplify this, this is m over Ta square multiplied by 400 square. But m over Ta square is 50 over 100 square. So 50 over 100 square times 400 square, it is 800. So what is the answer? The degree at time 400 time unit is 800. Okay? Is that clear? Okay, so let us do some curve fitting or line fitting. time 500 units, you're given the degree distribution of the nodes that join the network according to the BA model. Okay, so nodes join the network at these different time instants. And okay, so according to the BA model, nodes join at this different time instance, and you're measuring their degree at some future time 500 unit. Okay, so at that particular time instant, at time 500, this is the degree of these different nodes. Okay, so what we want to find, so this is what is given to you, the joining time and the degree at time 500. So what you want to find are the number of new links that get introduced into the network at each time a node joins. So that parameter m, so far we did not deal with it, so let us see. So m, the parameter m, which is number of new links, and exponent beta. Okay. Now, after we find the two, we can also find the degree of a node that joined the network at time 40. So there is some network that joined at time 40. So we want to kind of estimate what would be its degree at time 500 units. So it should be between 13 and 18. Okay, because 40 is between 25 and 50. The degree of that node that joined the network at time 40 is expected to be between 13 and 18. So we need to find it out. Is that clear? So how to do this? So first of all, we need to know what model is used. So this is a BA model. So we have to use the corresponding degree formula. So Ki of t is m times t over ti times beta. So what is given here? Ti is given, t is also given, and the degree is given. So the unknowns are m and beta. Okay. So you can solve this by just making two data point here from this, but we will try to use all the data point and try to kind of get a more accurate estimate. Okay, because this is experimental data. Let us consider like that. So it may not really fit. Okay, 100%. All right. So how to do this? We'll try to fit this as a curve or a line. So if I take logarithm on both sides, this is log Ki of t is, this is like what? A times b. So this is log m plus logarithm of this whole thing. Okay, so that will be, log of this is going to be, the beta can come before times log of t over ti. Okay, we did something like that before too. So this is like, so degree is given at different, for the different nodes at time 500. So that is like y equals some q unknown plus this. So this is our slope, beta times x. So this is x. Okay, so we have to decide which is x and y. Okay, so log of t over ti is your x, and the log ki at time t is your y. So t over ti, so t is 500 divided by ti. Ti is all the joining time. So it's like 500 divided by 10, 50, log 50. So all these are natural logarithms, the base e. So log 50 is 3.912. Then 500 divided by 25, 20. So log 20 is 2.996 and so on. 500 divided by 50, 10. So log 10 is 2.302 and so on. So similarly here, the log ki, so logarithm of these numbers would be this. So we expect a linear relationship between them. Okay, so you can take an Excel spreadsheet and try to fit. So I showed this already a few times. Okay, so you can practice. So once you plot the data right click on the data and say add trend line, and then go to the menu and ask you to display the equation. Okay, so it will display the equation like this. So y equals the slope times x plus the constant here. Okay, so this slope is our beta. So actually this is the log n. And slope is this. Okay, so slope beta is 5.67 as I write here. And first of all, it makes sense because this is according to the BA model. What was the formula? The original formula was, this is like I said, always beta is going to be half, right? And it's close to half. As I said, this is experimental data. So the other unknown, m. So how to get that? Log m is this 1.3651. So once you know that, you can find m. How do you do that? M is
Log
e to the power 1.3651, right? The base e. So if your calculator does not have an e option, or you don't know how to find e to the power something, you can use e to be 2.718. Okay, so e to the power 1.3651, the same as finding 2.718 raised to 1.3651. So that will come out to be 3.9. So it's always good to know the value of e. Okay, actually it does not end here. It is like it keeps on going, but we just use the first 3 decimal digit. Okay. So again, m is the number of new links that come to associated with each node joining process. So it has to be an integer. So we round it to the next largest integer. Okay. Any question? Okay, so now once you have found your m and beta, what can you do? Find the last part. So what you are required to find is at time 500 units, what's the degree of the node that joins the network at time 40 units? So you substitute all the parameter values. So m is 4 times 500. The joining time of the node is 40 raised to 0.5067. So that will come out to be 14.38. And this is again degree, so you can approximate to the closest integer, which is 14. Okay. So now you go back to the data and see if it makes sense. So the node joined at time 40, which is between 25 and 50. The degree of the node that joined at 25 time unit is 18, and the one that joined at 50 has 13. And so our node at time that joined the network at time 40 has in between 14. So it makes some sense. So if it is well above 18 or well below 13, you have made some mistake in the calculations that you have done. So that's the purpose of doing the last thing. You want to make sure the values of m and beta that you found make sense, because we found this 14 based on the values of m and beta, right? So you want to check if you can estimate the degree of some other node at some other joining time. Okay? Clear? Okay, so the other two problems are going to be similar to this, but let us do them. So this is according to the BB model. So this problem that we just did, we had one time unit t at which you measure the degree of all the different nodes, the different joining times. But in this problem, we have one particular node that joined at time 10 units. So the joining time is given here, and at some future time instant, all these future time instants, we are estimating or determining its degree. Okay, actually measuring its degree, so experimental data. So all these future time instants, we are measuring its degree. So, and the model is BB model. So what we want to find is the number of links, again the M, and the fitness of the node, because this is a BB model. Okay. So again, I asked you to assume the beta of eta I is same as eta. So assume the dynamical exponent is same as the fitness. Okay. So this is the formula, and we're going to assume this is same as eta. So what is given here? The degree of the nodes at different t values. Okay. And you're also given ti and t. So very similar to the previous problem. So if you take logarithm on both sides, log k, the degree is log m plus eta times log of t over ti. So what is given is t over ti, because we're given the different future time units, and the joining time ti is 10. And you're given the corresponding degree values. Okay, so what you have to do, plot this as a straight line, and you have to choose just x and y carefully. So again, the degree is the y, log degree is the y, and log t over ti is x. Okay, so plot them and try to fit the straight line and see what the equation is. So we get y equals this 1.452x plus this. So what is the slope? The slope is eta, isn't it? To go back to the equation that we just had. So this is the slope, eta. And log m is this q. So this is log m. So log m is 1.6116. So again, m is going to be e to the power of 1.6116, which is close to 5. And eta is 1.452. Okay. Now again, you can validate by doing something like this. Estimate the degree of the node at time 250 units. So the joining time is still 10, same node. And so you're given the degree of the node until time 200. So you want to kind of find what would be its degree at some time 250 units. Okay. So let us do that. So m is 5, t is 250, ti is 10, raised to eta, which was like some 1.4 something that we got. So if you do the math, so if you do the calculation, it will come out to be 535.5. So again, this is a degree value, so it has to be an integer, so 536. So now we can go back to the table, the data, and see if it makes sense. So we estimated the degree for that node at some time 250 to be 536. So it is above 388. Okay, if it's less than 388, definitely something is wrong. And also you can even go a little bit detailed. So for every increase in 25 time units, the degree increases by close to 50 to 60, around that. Okay, so this is increasing by somewhat like 60, and this is increasing somewhat like 65, like that. So this is an increase by 50. Oh, this is another increase. So this is again increasing by 65. So now from 200 to 50, right? It's twice this range. Here everything increases by 25, but here you're increasing by 50. So the degree should also kind of double. So the increase should be around 130 to 150. Okay, because again the exponent is greater than 1, so it's 1.452, so you expect the degree to increase faster, okay, with time. So this is around that, 388 and 536, so it's like 150 difference, okay? So if your number is like, why I said this, because if your number comes out to be 1000 or something much larger, again you have made some mistake in the calculation. So it cannot be too low or it cannot be too high. Okay?
So it should be around 388.
388 was the degree at time 200. So we estimated the degree at time 250 to be 536. So what I did so far is try to see if the 536 makes sense. It cannot be too large like 1000 or it cannot be like less than 388. If it is like 200 or 300, that means you made some mistake in the calculation. Okay? Because the degree should grow with time. So until 200 you have 388. So at 250 it should be larger. How larger? That's what we are trying to see. Cannot be too large. Okay? Okay, the last problem. So again, BB model. So consider a node that joined the network with 4 new links. So M is given here. Okay, so each newly joining node gets 4 new links. Joining time is not yet given. So some node I joined at time Ti with 4 new links. Its degree at some 2 future time instants, 100 and 200, are given as or determined to be 45 and 125. And here you have a function given for beta. So beta of eta I is eta square plus eta I. So that is the function of eta I. Okay. So you want to find the joining time Ti and the fitness eta I. So these are the 2 things that you have to find out. So what you are given is some node I join the network according to the BB model, and M is 4 new links, and its degree at some time 100 is given as 45, and at some other time 200 its degree is given as 125. Okay, so this is what is given. So, and you're also given the function beta of eta I is eta I square plus eta I. Okay, so how to solve this? So this is the formula for the degree according to the BB model. Okay, so write down the 2 degree values and the corresponding expression. So at time 100 its degree is 45, so its M is 4 times time 100 divided by Ti raised to beta of eta I. Okay, so let me do it here. So at time 100, okay, so this is given as M is 4 times time 100 divided by Ti raised to beta of eta I. Okay, and at time 200, that 125 equals 4 times 200 divided by Ti raised to beta of eta I. Okay, so what can we do? We can try to get rid of this Ti. Okay, so let us divide the second equation by the first equation or expression. So is 125 divided by 45. Now this side, if you divide, the 4 will cancel out. So it's going to be 200 divided by Ti raised to beta divided by 100 over Ti raised to beta eta I. Is that clear? Okay, so if I divide the second expression by the first expression, this is what happens. So we can write down like this. Okay, now the reason we did this is because we can get rid of this Ti, because this is like something over Ti raised to beta, again something over Ti raised to beta, so Ti can cancel out. Okay, so you simply have 125 divided by 45 equals 200 raised to beta eta I divided by 100 raised to beta eta I. So again, this is same exponent in both the numerator and denominator, so we can put them together. 200 over 100, right? Divided the whole thing raised to beta of eta I. So that means, so that is 2. So 125 divided by 45 is 2.78. So 125 divided by 45 is 2.78 equals 2 raised to beta of eta I. So we have to now solve first for beta of eta I. Is that clear? So how to solve this? You can take log of 2.718 divided by log of 2. Okay? Because if you take logarithm, log of this is, again the exponent can come first, times log of 2. So that's what is this. Is that clear? Okay? So if I take log of this log 2.78 equals beta of eta I times log 2. So I just bring this on the other side to the denominator. And that comes out to be 1.475. So what is 1.475? Beta of eta I. But beta of eta I is given as a polynomial. Eta squared plus eta I is 1.475. So you have to solve this like the quadratic equation. Okay? So if you bring this to the other side, it is eta I squared plus eta I minus 1.475 equals 0. So how would you solve a quadratic equation?
Minus b plus minus b square minus 4ac beta.
No.
Minus b plus minus root over of b square minus 4ac by 2a. Yeah,
Okay.
that's over there.
Alright, so if you have a quadratic equation ax squared plus bx plus c equals 0. The formula for the root of the equation is minus b plus r minus b square root of b squared minus 4ac, the whole thing divided by 2a. Okay. So in this quadratic expression, you have to identify the a, b and c and just substitute for them here. So a is 1, b is also 1, but c is negative 1.475. Okay, so minus 1 plus or minus. Now I discard the negative 1 because negative will make the fitness to be negative. So I take the positive sign. Okay, so plus square root of b square. So b is 1. 1 square minus 4 times a times c. So c is negative 1.475 divided by 2a. So if you simplify this, eta I comes out to be 0.813. Okay, so that's your fitness. So that's one of the two parameters you have to find, the fitness of the node. So the other thing that you have to find is the joining time. Okay, so how would you find the joining time?
Plug it back into one.
Plug it back here into one of the 2 degree equations given to you. Okay, so now that we know what is eta I, actually you don't need eta I. All you need is the 1.475, right? So we found beta of eta I, which is this, 1.475, right? So we can substitute for that here. So 45 equals 4 times 100 over Ti, the whole thing raised to beta of eta I. So that is 1.475. So again, you can use the logarithm as a basis to solve this, right? So this is Ti raised to 1.475. I just bring it this side is 4 times 100 raised to 1.475 divided by 45. Okay, so I just bring the t to this side and just bring the 45 to the denominator, and then just solve for this. So Ti will come out to be 19.38. So we can round it because time again is an integer. The joining time is an integer. So you can round it to the next largest integer. The reason we did not round to 19 is because it's greater than 19. So we should round the next largest integer. So that is 20. So what is that 20? That's a joining time of this node. So at time 20, it joined the network. And its degree at that time is 4 because it got 4 new links. And at time 100, you are measuring its degree, it is 45. Okay? So try to just see if the numbers make sense. So at time 100, its degree is 45, and at time 200, its degree is 125. So you could see the rate at which the degree grows kind of slows down a little bit, and that is because why? The eta is what? Is less than 1. Of course, the beta I is 1.475, so everything combined together. You don't have to really analyze much further. But eta is not that large, okay? But beta is a function of eta I, and the exponent is really 1.475. So the exponent is still greater than 1. Okay? So you should know how to solve a problem like this. Okay? According to the BB model. Okay, so we will do small world network, start this.